Hello, good morning.
Hi.
Yeah, uh, today I have one new student, Harsh. So, Harsh, could you please introduce yourself?
Yeah, hi, I'm Harsh Shetty. I just graduated from Stevens Institute of Technology. I did my master's in business intelligence and analytics. Before that, I was working for around 2 years in Mumbai as a business analyst at Endurance International. And right now, I'm looking for opportunities in the data analyst or business analyst domain.
Okay, okay. Glad to meet you, Harsh. So, in today's class, what I will do, because in the last class I discussed about the regression, I will continue this regression analysis. In the regressions, why I'm discussing these regressions, this thing is, in industry you will get one term. This is known as the predictive analysis, and the same time you will get another term is known as the prescriptive analysis. So what is this predictive analysis? Predictive analysis means you will get this data, and from this data you need to predict something. Let us consider you need to predict the price. uh, for instance, it's the price of oil. So this is the part of the predictive analysis. You are predicting. At the same time, let us consider you are supposed to predict the demand of product in a retail shop. So this is a part of the predictive analysis. Whereas when we are discussing about the prescriptive analysis, is very complicated. Why? Because you will get a case or the scenario, and from this scenario, uh, your algorithm will suggest something. Not only the predictions, it will suggest some solutions. For instance, uh, we can consider the route optimizations. See, you will give these informations to the your computers or to your algorithms, and from your algorithms, you will get the not only the predictions, at the same time some suggestions, what will be the correct route or what will be this optimum route, etc. So route optimizations, a lot of companies you will find they are means looking for candidate who has very good understanding or expertise in this route optimizations. So two terms, that is, one is the predictive analysis, another one is the prescriptive analysis. Now regression. So regressions you will the regression is when we are talking about this regression analysis. This regression is a very popular, to the data scientist, because at least 40 to 45% problems you will get, it's related to this regression analysis. And apart from that, we can expect to get 30 to 35% of problem related to the classifications. Now, what is this regression and what is this classifications? I discussed earlier. So I think it would be better if we discuss it again. The classification and regressions, both of them, are basically the part of the supervised learning. That is number one. But at the same time, you will find certain differences between this classification and this regression. What is this classification? For instance, you have two baskets. In one basket, you are having this apple and orange. So what you will do, that is, and another basket is empty. So you will pick all oranges from one basket, and you will keep it in the other basket. So, and after that, what you will do, you will use some label, that is, this is for this orange, this is for this apple. So anytime it means any, say for instance, any kid, he will call, the kid will check, okay, this is for this orange, this is for the apple, so he or she can easily detect it. Okay, this is for this apple, this is for the orange. Another beautiful example of classifications you can check, that is anytime if you means if you ask your mothers, just go to the kitchen and you will find that is all these, you know, the spices, or in means in India it is called this masalas. You will find your mother is keeping in different empty bottles, and so that means anytime you can easily find this salt or the pepper or the the sugar, etc. So this is one example of the classification. Now, technically speaking, there is classification is a means it's a supervised learning problem. In these classifications, we have these input data sets as well as a target column, because it is a supervised problem. But in this target column, this thing is, I told you repeatedly, that is, we will, instead of the continuous variable, you will find a discrete variable. Now, what is this continuous and the discrete variable? Say, for instance, discrete variable means in the target column, you will find that is these data set means these independent variables belongs to class 1 or class 2 or level 0 or level 1. So when you are getting these two levels, it is called the binary classifications. When you are getting these multiple levels, it is called the multi-level classification. Basically, a multi-level classifications is nothing but a part of the binary classifications. It is an extended part of this binary classification. So one beautiful example is the logistic regression. So you will get these extensive applications of these logistic regressions if you are willing to work in this healthcare unit. So I shared, two job, you can check this job description section. In the job description sections, you will find this new jobs available. I just shared these two. Few more jobs are available. One is in University of Miami. You can find that is they are looking for some people, who has a very good expertise in the healthcare sectors. Means the moment you will get this term, that is, you means some jobs are available in healthcare sectors, means please study prior to your interview, that is the logistic regression and the neural network, that is NN. These are the two important means you can expect to get at least 2, 3, 4 questions from this area. Now, classifications, one example I can say you have the data sets, and from the data sets you want to predict whether the person has the symptoms of COVID, yes or no. So this is basically binary classification. Now, when we are coming to this regression, it is the supervised learning. It is true, and at the same time, it has the input column, that is the independent column, and as well as this target column. In the target column, what is the thing is, in the target column, you will get the continuous variable instead of this discrete variable. Continuous variable means you will get the values means between this lower limit and this upper limit. When you are getting these values between these lower limits and the upper limits, means it can take any value between this lower limit and this upper limit. So this is about the means the fundamental differences between this regressions and the classification. So in the students class, what I will do, I will start with the means simple regressions. I will compare it, the simple regression and the multiple regressions. You can check this previous videos. Now the question is the previous videos you are getting everything? What is the means purpose of this class? This thing is in our class, I will discuss one thing more, that is called MLE. How can you use this maximum likelihood in regressions to find out the different values of these intercepts, as well as the gradient, that is this one. And at the same time, I will discuss about the certain aspects of the VIF and the multicollinearity and the regression diagnostics. So let us start with this one. So this is the standard error of estimate. Standard error of estimates is very simple. That is, you in regressions, you are getting only one value. That is the y hat value. We are saying that is, let us consider this y hat value is say this 10.5. Let us consider. But this thing is, instead of giving a discrete value that is 10.5, what we can do, we can give a span of these values. Let us consider this y hat value will be this in between this 10 and 11. The advantage of this is, the when we are saying that is this, the y hat value or the predicted value is in between this lower limit and this upper limit. So in every manufacturing sectors or in the shop floor, this is what people are expecting, that is the range, not the exact value. So within this range they will prepare the product, or they will prepare the dimension, etc. So standard error of estimates is basically, we are considering this Gaussian dimensions. In this Gaussian dimensions, that is plus minus sigma, plus minus 2 sigma, plus minus 3 sigma. So plus minus sigma means, plus minus 1 sigma means, that is 68% of these variations of this data you can get, and plus minus 2 sigma means 95.5% variations of data you will get, and plus minus 3 sigma means 99.7% variations of data you will get. Now, we will use these concepts to find out this upper limit and lower limit of y hat. So what is the standard error? That is SYX is basically the square root of y minus y hat whole square, summation of that, divided by the degree of freedom, that is n minus k minus 1. What I am doing, I'm considering the y hat is equal to beta 0 plus beta 1 x1. So if you are considering only one independent variable, so it is the degree of freedom is equal to n minus k minus 1. So k is equal to 1, so n minus 1 minus 1, so n minus 2. So denominator we are considering. Now, this is this hand calculations. If you check, this data is given and corresponding, the regression equations is given, that is 24.44 plus 1.889x. That is this y hat. So this is basically, the simple regressions. Now, simple regression is nothing but this equations of a straight line. So what I'm doing, that is x value, that is y value, y hat value, I'm calculating from this given expressions. Say if x is equal to 40, then what will be the value of y hat? And this way we are calculating. Next, what I'm doing, that is I'm calculating this y, the difference between y and y hat. Then I'm calculating this the square of this one, that is y minus y hat whole square. And after that, I am calculating this, the sum of y minus y hat whole square. So this is this equation of this regression line. Now you can calculate the standard error. Standard error is y minus y hat whole square, its sum. So this sum is nothing but 378, and divided by degree of freedom, how many observations you are having. That is 1, 2, 3, 4, 5, 6, 7, 8. So 8 minus 2. So 8 minus 2, you will get, this is 7.9. So if you consider this 68% confidence level, means this is the 68% plus minus 1 sigma, 68% confidence level. So in that case, so what will happen? That is y upper is equal to, that is y hat value. Let us consider x is equal to 70. So from this y hat value, this is 24.44 plus 1.889 multiplied by 70, you will get 157. So 157 plus 1 sigma. 1 sigma is equal to 7.9, so 164.9, and y lower will be 157 minus of 1 sigma, that is 157 minus of 7.9, because sigma value is equal to 7.9, so you will get 149.1. So if you are considering the 68% confidence level, so instead of 157, you are getting, that is y hat plus minus 1 sigma. So the value will be 164.9 and 140.9, 49.1. So this is the range of this y hat. If you are considering this 95.5% confidence level, so in this case, this y upper is 157 plus 2 sigma, 157 minus sigma. So this value will be this 172.8 and 141.2. Okay. So this next is this simple and this multiple regressions. In this multiple regressions, what is this expression of this y? Y is equal to beta 0 plus beta 1 x1 plus beta 2 x2. And in case of the simple regression, this is y is equal to beta 0 plus beta 1 x1. So this is this equation of the straight line. But when we are considering this two dimension, means these x1 and x2, these two independent variable, and y, instead of a straight line, we are getting a plane, equation of a plane. And see, if you extend this line, this is this intercept. So in this case, this plane will intersect this y-axis at the point of alpha, that is this intercept. And at the same time, it will make some angle with this x1 axis and this x2 axis. This angle is nothing but this beta 1 and this beta 2. And this is basically is known as this response plane. Now this is a straight line, this is a plane, and these are the points. From these points, if you draw the projections onto this line, so this length is basically this error. So our objective is to reduce or to minimize the sum of this length. Similarly, we are doing this sum of this length, sum of these projections we need to reduce. So this is the basic difference, if you use this coordinate geometry, this is the basic differences between the simple regression and this multiple regressions. But this thing is, if you increase this dimension, say for instance, x1, x2, x3 up to xn, in that case, it would be very, very difficult for you to, use the graphical presentations. Now, what is this multiple regressions? That is, this is the simple equation, that is y is equal to a plus b1 x1 plus b2 x2 up to bk xk. So x1, x2, x3, xk, these are these independent variables. For sake of simplicity, if I consider this k is equal to 1, so these multiple regressions will become a simple linear regression, that is y equal to a plus b1 x1. So what I'm doing, I'm considering a simple linear regressions, multiple regression, that is y is equal to a plus b1 x1 plus b2 x2. So summation of y is equal to number of data points. So na plus b1 summation of x1 plus b2 summation of x2. You will get this expression. Now, if you multiply with x1, so summation of x1y plus a summation of x1 plus b1 summation of x1 square plus b2 summation of x1 x2. But if you multiply it with x2, so you will get summation of x2y plus a summation of x2 plus summation plus b1 x1 x2 plus b2 summation of x2 square. So these are the three equations, three unknowns, that is a, b1, b2. So let us try to solve this one. So x1, x2 and y is given. So I will do this hand calculations. So this is the, three expressions, summation of y this, summation of x1y, summation of x2y. So what I'm doing, x1, x2, y, x1 square, x1, x2, x2 square, x1y and x2y. And this last row is basically their summation. That is 4 plus 7 is 11, 11 plus 9 is 20, 20 plus 12 is 32. So this way you will get it. So these values, you just put it here. The summation of y is 56. So 56, some NA, how many observations you are having? 1, 2, 3, 4. And this one is, I'm considering only the 4 data points. Okay. So, and this is basically the sum of x1, x2, x1. So you discard this one. That is 4, 7, 9, 12. So 4 observations we are having. So 4 observation is 4a. So b1 plus summation of x1. From here you can also say this is equal to 32 plus B2 is summation of x2, that is equal to 16. So this way you prepare these expressions, then you just do simple eliminations and you will get this value of A, B1 and B2. And this is the expressions of Y, where you will get Y is equal to A plus B1x1 plus B2x2. So A is equal to 0.644 plus B1 is 1.661x1 plus 0.0169, that is B2. Now, the next thing is, how can you find out the multiple regressions R square value? This R square value we calculated, during the simple regressions. R square here is nothing but this formula we are using, that is yi minus of y bar, that is this average, whole square, minus of summation yi minus of y hat whole square divided by summation of yi minus y bar whole square. This is basically 1 minus SSE divided by SST, because R square is equal to SSR divided by SST. So SSR is equal to SST minus of SSE. This is SST minus of SSE divided by SST. So 1 minus SSE by SST. So this is this expressions of this y hat. So what I'm calculating, x1, x2, y hat, yi minus y bar, yi minus y bar whole square, yi minus y hat, and yi minus y hat whole square. So if you sum it, you will get this 98. So this is this 98 minus of 2.44 divided by 98. So you will get 97.5%. So 97.5% of the variability can be expressed by this expression. This is okay. Now, another term I told you repeatedly, that is when we are using the multiple regressions, the very important term is adjusted R square, not the R square. That is this adjusted R square. The adjusted R square is this advantages. Say we have in this expression, that is x1 and x2. Now questions will come to your mind. That should I use x1 instead of using this x1, x2? Should I use this x1 or x2? How can I determine? So you will do, that is, let us consider this is the model number 1. The base model, you are using this x1 and x2. Okay. And in this model number 2, you are using only x1. So in the model number 1, calculate adjusted R square. In the model number 2, calculate adjusted R square. Now, if you check, that is this adjusted R square value is reducing. So definitely, so it will confirm that is x2, because you are eliminating x2. x2 is strongly influencing this y hat. Okay, so R square value cannot say that is how the x1 and x2 are related with this y hat. The moment you are getting this R square, adjusted R square value, so it can say how this means y hat value is connected with this x1 and x2. Now, this next one is these significance testings, means using this Anova table. This Anova table, the same concept, just like the simple regressions, we are considering null hypothesis and this alternative hypothesis. And this null hypothesis, we are considering that is all the coefficient, that is B1, B2, B3, etc. All of them are equal to 0. So it means this y cannot be expressed as a linear expressions of x1 and x2. Y is basically an independent of x. And in this alternative means expressions hypothesis, we are considering the bi, that is the b1, b2, b3. These are not equal to 0. Okay, so in this case, what we will do, we will basically use the same simple multiple regressions Anova table, just like this means we discussed this earlier for the simple regressions. So these are the data sets x1, x2, and y. Say this is the summation, basically this 32, 16, and 56. This is, if you sum it, that is 20, 37, 49. I think this data is wrong. This data is wrong. So don't use this last data. So means you can consider only these 4 observations and you can do it. Okay. So what I'm doing, that is in this case, I'm preparing this table. I'm calculating SST. I'm calculating SSR. I'm calculating SSE. And at the same time, what I'm doing, I am calculating this degree of freedom. The degree of freedom for these SSR, that is 95.56, is equal to n minus k minus 1. That is number of observations 4. So 4 minus k, that is x1, x2, two independent variable, 4 minus 2 minus 1. So the degree of freedom is basically 1. So here you will get this one. So 95.56 divided by its degree of freedom, 4 minus 2 minus 1. And next is this, that is SSE, that is 2.44 divided by its degree of freedom. This degree of freedom is 2. So definitely, so F value, if you calculate, so you will get 19.58. Next, what you need to do, this you need to calculate this F critical from this distributions of F, that is from this F table. You need to get this value. For that, you need the numerator, what is this numerator degree of freedom and the denominator degree of freedom. So the numerator degree of freedom and the denominator degree of freedom you need to calculate from this F table. I discussed earlier, so that's why I put a question mark here, how to do it. So you please check this is your assignment. You please check this previous presentations of the simple regressions. I discussed about this Anova table and calculate this F critical means F critical value from this F distributions table. Once you get the value from the distributions table, then what you need to do, just compare. So whether if F critical is greater than this F value that you have calculated from this ANOVA table, then what you need to do, you need to accept this null hypothesis. And if this F critical is less than this F, then you need to reject this null hypothesis. So in this case, it's 19.58, and you will get a lesser value. So what you need to do, you need to reject this null hypothesis. It means so at least one coefficient, that is beta, is not equal to 0. So y can be expressed in form of x1 and x2, either x1 or x2. So there is a linear relationship between this dependent variable and independent variable. So this is basically known as the significance testing of multiple regression. Now, what is this partial regression coefficient? So partial regression coefficient, this is your expression. So here you will get this B1, that is 1.661, and B2 is equal to 0.0169. So if B1 is 1.661, what is the significance? Means what is this concept of this B1? So B1 is known as this partial regression coefficient. It means if you increase x1 by 1 unit, then the value of y will be increased by 1.661, considering x2 is constant. Considering x2 is constant, so if you increase x1 by 1 unit, then the value of y will be increased by 1.661 unit. So similarly, if you increase the value of x2 by 1 unit, keeping x1 is constant, then the value of y will be increased by 0.0169 unit. So this is the concept of partial regression coefficients. Means if you check these equations, this coefficient is very, very important. You can easily say that is x1 is contributing more than x2. So x1 is very, very important factor here. Okay. So this is all about this partial regression coefficients. Now what I will do, I will try to understand this a little bit of mathematics behind this multiple regression. That is y is equal to beta 0 plus beta 1 xi1 beta 2 xi2. What is this I? I is the ith observation, and 1 is the independent variable 1, 2 is this independent variable 2, this way. And at the end, I'm considering this epsilon I. This is basically this error term. This error term is this IID. I discussed this IID because in what is called central limit theorem, you will get this concept of this IID. When means law of large number, that is when n tends to infinite, means large number of IIDs we are considering. So this IID is basically tends to follow a what is called the Gaussian distribution. So in this case, what we are considering, this error term is basically independent, means epsilon error, this error 1 is independent, error 2 is independent. There is no dependency, there is no autocorrelations. This autocorrelations you will find in this time series analysis. And what we are considering, that is the n is the Gaussian distribution. It will follow the Gaussian distribution with mean 0, and the standard deviation is sigma square. And next, what we are doing, I said repeatedly, there is the multiple regressions. The basically the supervised learning is nothing but the optimization process. So in this case, what we are doing, it is basically at the loss functions, we can say, that is this error term, that is actual value, that is yi, and this is the predicted value from the regression equations you are getting. So the square of this, I is equal to 1 to n, this is equal to q. This is the error square. Why you are doing the square means, to eliminate this effect of the sign, that is a positive sign and this negative sign. Now, because it is, we need to find out this beta vector, or the values of beta 0, beta 1, beta 2 this way. So this is the partial derivative of del q by del beta 0. So this one, this should be equal to 0, because you need to find out this maxima or minima. And this is del q by del beta j is equal to means 1, 2, 3, 4 this way. So you will get this is equal to 0. So this is a very simple concept. Now, this is important for your, what I say, for this interview. In every interview, you will get this question, that is express these multiple regressions, and they will expect this the candidate should mention this matrix representations, that is y1, y2, yn, that is basically a column matrix. This is a vector, we can say. And this is a design matrix we discussed earlier, that is first column is 1, and this one is x2 xn. This is this error, and theta is equal to theta 0, theta 1. So x theta, this is 1 x1, this one, multiplied by theta 0, theta 1. You please check this matrix multiplications, you can check it. So you will get, after multiplication, is theta 0 plus theta 1 x1, theta 0 plus theta 1 x2. So this way you will get. So we can express it as this y is equal to x theta plus the error term. This is the matrix representation. Now, when you are coming to this mean square error, I discussed earlier, this is equal to e theta, that is y minus of x theta, that is MSE is basically this 1 upon n E transpose E, and you need to minimize this mean square error. So del of MSE divided by del theta, means with respect to d theta, you are differentiating, not the divide. So you will get this theta optimum value is x transpose y multiplied by x transpose x minus of 1. So this is important, and we will use this is extensively in this during the study of the MLE also. So hand calculation. So I am considering a x value and the square of this, that is x square value, and this group, and I will use this matrix representations to understand it. So x will be, that is first column is 1, this is x value, this is x square value, this is y. So you can check this one. So next is what I will do, that is this beta vector. Beta vector is equal to beta 0, beta 1, beta 2, is nothing but the x transpose x inverse, that is x transpose y. So this is this matrix you are getting, that is x transpose x inverse, this one. And this is x transpose y. X transpose means that is row and column you will exchange. That is, see, X matrix. So here 3 columns you are having. So the X transpose will have the 3 rows. So this is X transpose. So you are getting 3 rows, and these are the values. This is this Y. So you need to multiply all these. So finally you will get this, this, and this. It means this beta 0 is this, beta 1 is this, and beta 2 is this. So this is the matrix multiplications, because it is easy to multiply this matrix. We are doing it extensively in this sklearn, and it is expected you will code in this way. So this equation of this regressions line, finally you are getting, that is beta 0, beta 0, beta 1, and beta 2. Okay. So regression diagnostic means when you are doing this multiple regressions, first of all, what you need to do, you need to keep in mind that is this error term. First assumption is this x1, x2, these are the independent variable, then they will follow the Gaussian distribution. So summation of the Gaussian variables, this RV, the random variables, will definitely create a random variables with the Gaussian distribution, means y must follow the Gaussian distribution. This is the first assumption. Next assumption is when you are considering this error, that is this residual error. So this one, check for linearity, the plots of the residuals against individual predictor variables. So what you need to do, along y-axis, you will consider the residuals. Along x-axis, you will consider this, the predictors. So x and y, when you are considering, so you need to plot it. So check for constant variance, that is whether it is homoscedastic or the heteroscedastic, that you need to check. A plot of the residuals against the fitted values means along y-axis residuals, along x-axis you need to consider this predicted value. And you need to check, is there any relationship with this residual error and the predicted variables? Now check for the normality. This is basically the quantile plot, QQ plot, a normal plot of the residuals. You need to check whether this residuals is following the normal distribution, yes or no. And remaining 2 points, you can do it. That is, check if the random errors are autocorrelated. Means that is epsilon 1 and epsilon 2. Is there any relation between epsilon 1 and epsilon 2? So if you find any autocorrelations, you cannot use this ordinary least square. See, plot of the residuals against any omitted predicted variables. Plot of the residuals against any omitted predicted variables means if you guess any predicted variables, in this case, you need to consider y-axis is the residuals, along x-axis you need to consider that predicted variables, and you need to plot it. Now this is the multicollinearity. Now what is this multicollinearity? That is, multicollinearity means you are having this y is equal to beta 0 plus beta 1 x1 plus beta 2 x2. So x1 and x2, our assumption is expected to be independent. There will be no relation between x and x2. But in a real problem, you will find this x1 and x2 are correlated. Means if you increase x1, so x2 will increase. If you decrease x1, so x2 will decrease. So this is called the multicollinearity. And what is the effect of this multicollinearity? See, technically speaking, during this interpretation of y, you will face the problem. So what I am saying, that is, there is y is equal to beta 0, beta 1 x1 plus beta 2 x2. So if x1 and x2 are independent, so what I will say, they consider x2 is constant, then we can say for unit change of x1, the expected change of y is equal to beta 1. Isn't it? Just now I said there's a partial regression coefficient. But now the problem is this x1 and x2 are correlated. So you cannot say that's keeping x2 constant, because we need to analyze this effect of x2 on x1. So the simple approach is, or the thumb approach is, you need to remove x2 from your equations. So if you can remove this x2, so it's okay, there will be no effect on this regression equation. Now there is questions will come to your mind, means when you are removing any independent variable, is there means any loss of information? So this is very, very important in this multicollinearity. So multicollinearity, you will keep in mind, that is, it will create a problem during these interpretations of y, the predicted variable. In some books also you will find that it is creating some effects on this accuracy. And today's class I will show you, I will use this Boston data. In this Boston data, what I will do, I will show you that is this error is also will be affected when you are using because of this multicollinearity. So detecting this multicollinearity, that is, the simple thing is we need to develop a curve matrix, covariance matrix, that is R value we need to check. If it is close to -1 or +1 means this X1 or X2 or Xi or Xj are highly, correlated. So we need to remove one of them. So this is the curve matrix. And what I'm doing, I am initially doing this scatter plot. See, if X1 and X2, that is this X1 and X2, X1 and X2, that is the sigma 2, 1, and X1 and X2, this is sigma 1, 2, sigma ij is equal to sigma ji. So these two terms you need to check. If you check this means close to 1, means sigma 1 and sigma 2 are highly correlated. You can go for this scatter plot, you can get this type of means plot here. Now, if you find that is X1 and X3 are highly correlated, so you need to do this scatter plot and you need to check. And if you plot this X2 and X3, if you check this one, they are not correlated at all. They're independent with each other. So in that case, in this equation, you can keep this X2 and X3 because they are independent, but you cannot keep X1 and X2 simultaneously. So what you need to do, you need to write a code, and this code you need to calculate this curve, that is covariant matrix. This is the covariant matrix for all these features or the independent values. And then you can check whether automatically you can check any value is close to 1 or not, then you need to remove it. Now, detecting multicollinearity. So one approach is called this variance inflation factor, that is called this VIF. That is VIF is equal to 1 by 1 minus R square J, where R square J is the coefficient of the determinations, means R square value. Just now I showed you that is how to calculate R square value. This coefficient of determinations of the model that includes all the predicted except this J predicted. Now, what people are saying that is if VIF value, that is variance inflation factor, variance inflation factor is greater than equal to 5, means this multicollinearity is predominating. It is greater than equal to 10, that is greater than equal to 10, that very severe multicollinearity effect you can expect to get. So this one. Okay. So this all about the presentations of about this multiple regressions. Now what I will do, I will share, now I will share the code which is important for us to study the multiple regression, as well as so when we are studying this regressions now, first of all, the simple regressions you will hardly get. Mainly you will get the problem related to the multiple regression, and multiple regression, that's why is very, very important, because multiple regressions, when we are discussing the multiple regression, is basically is basically mainly problems in the real problems are basically the multiple regressions in nature. Now what we will do, there is multiple regressions. I think the 68 different approaches you can find, 68 different approaches to use for this multiple regressions, to solve a multiple regression problem. Now, first of all, when you are trying to solve a multiple regressions problem, one is called the top-down approach, another one is this bottom-up approach. What is this top-down and the bottom-up approach? So top-down and bottom-up approach is basically, in the top-down approach means you will consider the all independent variable like the x1, x2, x3, x4, etc. Means from the data set, and after that what you will do, say you need to remove variable one after another. So let me share the spider. Okay, so are you getting the spider now?
Yes. I can see
Okay,
it.
great. So let us start. So this is the VIF and this multicollinearity. So what I'm doing, I'm using the Boston data set. That is Boston data set. We need to predict the price of the houses. So what we will do, so in this Boston data set, some data means some fields are very closely correlated with each other. So we need to remove it. So we need to calculate the first of all is very, very important. That is the VIF. So when you are calculating this VIF, here you can find there is this two field is RAD and TAX. That is their fields are very closely related. There is one value is 8.1 and another one is this 9.8. So 8.1 and 9.8, if you find that is almost close to 10 and means it is greater than 5. So we need to remove it and we need to, recalculate the regression equations. So what I'm doing, now the questions will come to your mind. Should I remove this RAD or should I remove this TAX? The thumb rule is don't remove this TAX. Instead of this TAX, you can remove this RAD. So it is your choice because the second highest point you should remove instead of this highest point, because it may bring some error to your model because certain things, for instance, this VIA, why people are considering this, if the VIF greater than equal to 10, that is severe multicollinearity problem will occur. Now in Carnegie Mellon's lecture notes, you will find they clearly mentioned there is no exact explanations behind it, why people are considering it, but people are using it in this industry itself. So that's why we can follow the same things. I should say that is instead of means removing the TAX, you can remove this RAD. However, I would request you create the model, you remove TAX, TAX, that is this highest VIF value, and you calculate this model regression line equations and this model summary, and you check means the change in accuracy. So what I'm doing, I am in a very simple way, what I'm doing, that is first of all, I'm using this sklearn.dataset, that is the Boston dataset. So you can download this Boston dataset from this Kaggle and you can do it. Then it means splitting this X value and this Y value. That is where X is this independent variable, Y is the target column. And after that, I'm importing this sklearn. This is not a correct approach. So this import and from these two statements, what is this meaning? When you are importing this sklearn, means this sklearn basically it contains several classes, several .py files. So it will load everything to the computer memory. And when you are saying there is from sklearn dot model selection, model underscore selection, import train test split, basically you are means calling a particular method or a particular class you are loading to this memory, not this entire sklearn. So this one is usually preferred to the data scientist because you are not killing this memory. Okay, so why train test split is important? Because when you are getting the data set, so 7 essential steps of the data science as mentioned by these Google practitioners, that is first one is load the data. Number 2 is once you load the data, then you pre-process the data. The pre-process means you remove the outliers, you remove, you change the format, you transform the format, normalize the data set, etc. All the stuffs you need to do.
I want to ask one question here. It says import the train test split. Does this mean this is using for when we load the data set, we need to separate the data we want to train the model, and the rest of the data we use for test the model?
Yes, absolutely correct. Absolutely correct. Because we are getting a chunk of data. And this chunk of data sets, we cannot give it to this model directly. So what we will do, we need to split it. Split is 80-20%, this Pareto analysis, all of you know. This same thing we are doing. That is 80-20 we can do, or in some cases we can do this 70-30. This 80% or 70% will go for this training, and 20% or 30% will go to.
But how do we decide like how much percentage we need to use for
Yes.
testing? How do we decide this percentage? It doesn't really.
Yes. This is a very important question, because when we are saying that is 80-20 or 70-30, so the thing is this: how much data, means how much rows you are having this in this actual data sets. Means when you are doing it, say let us consider you have the 100 rows. So 100 rows means 80% of it, means 80 rows you are giving it for this training, and 20 rows you are giving it for the testing. Now this thing is, if you are having this minimum number of rows, in that case this problem is very few rows you are dedicating it for this testing. So in that case, if the number of rows in this testing is very limited, very small, that's in that case you may face a problem. So how can you find out this optimum value of the training and testing this splitting? This thing is, in industry, a lot of things you will find is people are following is mainly because of their from their experience or from the searching the work of the different people. Say for instance, this VIF value they are considering should be equal to greater than equal to 5 or greater than equal to 10 is very severe. Similarly, they are saying that is, if it is the percentage value is 20%, then it is okay. If it is means very small amount of data, then you can go for 70-30 divisions, etc. Now this thing is, apart from that, we need certain specific approaches, and these specific approaches I will show you. That is, it's basically that is it is basically a multiple criteria decision analysis part, how to consider, means how to divide the training and testing data. So when you are dividing this training and testing data, there is another term, please note it down. It is known as the cross validation, that is CV. K-fold cross validations often it is called. There is two approaches in this industry. One is called the K-fold cross validations and the random search cross validations. K-fold cross validations means you have the chunk of data sets, and from the chunk of data sets, you are randomly selecting, a certain part of the data sets, and you are giving it to this model, and you are getting this result. And after that, you are averaging this result, averaging the score, so averaging this accuracy. So this is called this cross validations. And another one is called this random search CV, this cross validations. This is basically, this is faster than the grid search CV. The previous one is the grid search CV. Another one is the random search CV. The random search CV is much faster than the grid search CV. Basically, we will use this grid search CV as well as the random search CV extensively for the hyperparameter tuning. I discussed about this hyperparameter tuning during the study of the decision tree. So hyperparameter tuning, these methods you can use, but the problem is when you are using it, if your data set is too big. Now, in that case, you cannot use this random search CV or this grid search CV, because it will take a lot of time. If you have this GPU, means in your laptop or desktop, you need to use this GPU for random search CV or the grid search CV. So in that case, what you need to do, another package is available that is known as Thunder CV, THUNDER, Thunder CV. There is Thunder cross validation. This is the only package available at present that you can connect with this GPU. Otherwise, you need to write your own code to connect this GPU with this one. So this is about all the cross validations. Now, from sklearns, you can import this linear model, because we are going for this regression, so linear model. So import statsmodel.api. The stats model is basically for the ordinary least square regression, that is SM. This import numpy as NP. And next is what you are doing, that is X is this independent variable, collection of this independent variable, and Y is basically the dependent variable. Now what you are doing, that is sklearn dot model selection dot train underscore test underscore split. So I am passing this independent variable, dependent variable, and how you will divide it. That is 20% of the data you will take it. Okay. And this 20% of data will go for the testing, and remaining 80% of data will go for the training. Always remember that for the training, we need to give the large amount of data. And the random state, because randomly it will select, that is random state is 5. And this is basically the key to keep in memory. That is how you are dividing it: X train, X test, Y train, Y test. Now, model is equal to SM. You are instantiating this class, that is ordinary least square. You are passing this Y train and SM dot add constant, that is to create the design matrix, that is X train, and you are feeding it in a single line. I did it. You can separate it. Like first you instantiate this model, that is sm.ols y train, sm.add constant this, passing the variable of y and x. Then in the next step, you can do model.feed. So it will feed the model. When it is feeding the model, is basically the computing, means all the necessary calculations, means regressions lines, etc. it is finding. Now next is model.predict, that is sm.add constant this x test, that is this testing data. So you will get this predicted value. Now print model.summary. This model.summary means this is the statistical analysis results you will get here. Now this is very, very important. The statistical result you are getting, that is from this model summary, and only ordinary, means this stats model can generate it, because scalar linear model you can use this, you cannot get these results. In that case, you need to write code and you can generate it. So on the top, it is given this dependent variable, this MEDV method, ordinary least square, R square value is 0.738. Okay, and adjusted R square value is 0.730. So you can check this R square value is very, very poor. Only 73.8% variability you can expect with this one. Now, one reason would be that is I jumped the data pre-processing part. That is, I load the data. The next step should be the data pre-processing. So data pre-processing, I didn't check. Maybe it contains, you know, some missing values. Maybe it has some outliers. So all the stuff we need to check. In that case, this accuracy or this R square value will be increased. Now, adjusted R square value is 0.730. Now, I am using the top-down approach. Means I will consider all the independent variables, and then I will remove independent variable one after another, one after another. This is a top-down. And the bottom-up is you start with one independent variable, and then you add independent variable one after another to the base model or the starting model. Okay, the base model, this term you will get repeatedly in this industry. So this F value is 84.65. Log likelihood, this is our topic today. I will discuss archaic information criteria and Bayesian information criteria, AIC and BIC. We will discuss all the stuff. And this is the coefficient, standard error, T statistics, means T testing, and probability of this one you are checking. And this is Darwin-Watson testing. This basically, if I recall, this is for to make the data set estimate stationary. We will discuss this one later during this time series analysis. JB testing is important. This skewed or not, the skewed data means whether positively skewed or this negatively skewed, means the Gaussian distribution, it is not following the Gaussian distribution, it's deviating from this Gaussian distribution. So that's why what we will do, we need to change the skewed distribution to the Gaussian distribution. And the kurtosis is basically this, whether it is mesochatic, leptochatic, platychatic, etc. That is mesochatic means Gaussian distribution. These the perichatic and this leptochatic. Perichatic is means is very peak, is the beta Karl-Pearson coefficient is greater than equal to 3, greater than 3. So all the stuffs we need to check here. Now the thing is, after that, what I'm doing, I am just calculating this VIF, how to calculate this VIF. Now this is important. Now what I will do, this from stats model, stats dot outliers influence, import variance inflation factor. So from stats models, stats dot outliers influence, import variance inflation factors. Then I'm creating a data frame, pandas data frame. Okay, now one thing, this if you face any coding like this statements, creating data frame, the data analysis part, simple code, if you need, or if you any class, you please let me know. I will explain line by line. Even I will write the code in the class. That is live demonstration, it will be, and I will show you how to do it. That is VIF is basically this PD, import pandas as PD. So pandas toolkit. So PD dot data frame. So you are creating a data frame, a null data frame you are creating. Now, after that, you are adding this column name, that is the VIF factor and features. What I'm doing, say variance influence factor, it needs this X underscore temporary values. What is temporary values? Now, X temp is nothing but sm dot add constant X temp. I am creating a temporary variable and I am passing these means design matrix to this temporary variable. And then this is comma I for I in range X underscore temporary dot values dot shape one, means it will take all the columns and it will put one after another to the variance influence factor, and it will check the VIF factor value, and it will put the VIF features, means the temporary columns. Now, if you check, this is a script. In a script, I am running a for loop in a single line, and this is third bracket, means you are creating a list finally. Finally, you are creating a list and you are assigning this list to this VIF factor column. And after that, you are printing this VIF. This VIF is a data frame. Round one means to 1 decimal points, you are means printing it. So this is 1.7, 2.4. This way you are getting. Okay. Now this thing is, I need to remove RAD. So the data sets dot drop the column name, and after that I'm saying this x is equal to 1. When you are saying this x is equal to 1, means this column, this is very, very important. When after removing an entire column, you must say x is equal to 1. Otherwise, the matrix may be distorted. So x is equal to 1 means column will be remain as earlier as before. Means at the same time you are assigning it to a new variable Boston underscore new. Instead of that, you can do this Boston underscore features underscore df dot drop this x is equal to 1 comma in place equal to true. So it will be updated immediately. But what we are doing, we are not touching the original column, means original data frame, and I'm creating a new data frame. And after that, I'm printing this Boston underscore new dot head. So it will print 5 rows of the data set so that you could check, well, the column is RAD, whether it has been removed or not. Next, what I am doing, I am separating, that is X1, that is independent column, and the dependent column. And then I am dividing it, that is training and the testing data. And after that, what I am doing, I am calculating this variance inflation factor, and I am calculating these features, and I'm printing it with the model summary. So if you print it here, so this is VIF. If you check this one, that is the VIF value. If you check this VIF value is basically, it's changed almost. That is, there is no effect of a means multicore linearity. Now the RAD value, sorry, the tax value is 3.6, because earlier RAD value is was 8.1 and tax value was 9 point something. So you can check it from here. That is 9.8. Now it is reduced to 3.6. Now, if you check this model summary, that is R square value reduced to 0.724 and adjusted R square value reduced to 0.715. Now, the thumb rule is, if you say, sir, R square value is decreasing, earlier it was 73%, now is 72%. So R square value is reducing, means you are deteriorating, you're spoiling this model. Now, this thing is, this R square value has no effect on this model when you are considering this multiple linear regression. I told you repeatedly, this thing is, the instead of this R square value, you need to consider this adjusted R square value. What is this adjusted R square value? Adjusted R square value in the denominator, you will get n minus k minus 1 term. N is this number of observations, k is, what is called the number of independent variable. So if you are removing RAD, an independent variable, you are reducing k. So let us consider earlier n minus k minus 1 was 9. Now you are reducing n minus k1, making this n minus k minus 1 to 8. So earlier it was 9, now it is 8. So a number divided by 9 and a number divided by 8. So definitely when you are saying there is a number is fixed, divided by 8, its value will increase. And what is adjusted R square? That is 1 minus of some term divided by n minus k minus 1. So when you are increasing this n minus k minus 1, that is 1 minus the entire term is increasing. That is 1 minus this term is basically decreasing. So that's why this adjusted R square value is decreasing here. Similarly, in this R square, what is happening? R square is basically, that is SSR by SST. When you are calculating this SST, that is thing is mean value is important. But you are removing one column, how you are getting this effect on this adjusted, means R square value. Yeah, well, we will definitely get, you will get this effect on this R square value. This thing is, the R square value is SSR by SST. SSR by, SSR by SST, or 1 minus SSE by SST. So SSE is Y minus Y predicted value. Now, if you change this Y predicted, because the predicted value you are changing, earlier it was Y is equal to beta 0 plus beta 1 x1 plus beta 2 x2. If x2 and beta 2 is positive, so definitely Y is, means some value you are adding to Y. Now, if you are removing beta 2 x2, this predicted value is decreasing. Am I correct? So when you are decreasing Y hat, so definitely this value, this SSE value you are increasing. So 1 minus SSE by SST. So if you are increasing this SSE, so definitely 1 minus SSE by SST will decrease. So this is the actual effect you will get here. So that's why this value is changing. Now what I will do, so I will, next I will calculate the mean absolute. That's why I will calculate the mean absolute error and mean absolute error for the new model, mean absolute error of the base model. So in this case, you will find the value is 3.21, and in this case, this value is 3.13. So earlier you were getting 3.21, now you are getting 3.13. So this value you are changing, and definitely if the error value you are reducing, so definitely because of the multicollinearity effect, the error value earlier was 3.21. Now you are remove this RAD term or RAD column or RAD features, so this error term is increasing. So definitely we can say the multicollinearity has certain effect on the error term. That is number one. This is very, very important. Now next thing is this regression diagnostics. So when you are coming to this regression diagnostics, the sklearn has several terms. The first one is the JB test. JB test means when you are doing this JB test, you will get this JB test value, chi-square value, skewed value, kurtosis value. Now how to do this JB test? That is, I am considering a list. In this list, I am mentioning there is the name of the different tests, like the JB test, chi-square test, skew, kurtosis, and after that what I am doing, that is SM, that is this stats model, that is sm.stats.jb test. Then the model, what is this model? Now you have fitted the value to this model. Model means you are instantiating. Here you can check, that is sm.ols, means you are instantiating this OLS. You are passing this Y train and this add constant, and you are feeding this model. You are getting this model value. Now, this model has certain residuals, and this residual ID you are considering here, and you are passing to this JB test, and then you are doing this LGIP. LGIP is nothing but, you know, the GIP function. The GIP function is basically, it will create this ordered pair. Say A is a list 1 and 2, it has 2 values, and B is a list, it has the 2 name, that is Hari and Ravi. So if you GIP A and B, so it will create the ordered pair, means it will take first element from A and first element from B, means it will create an ordered pair like 1 comma Hari. Next ordered pair would be second element from A and second element from B, that is 2 comma Ravi. So this is the JIP. So this is the long JIP. LJIP we can consider. LJIP is basically most probably this long JIP, and we are getting this one, that is LJIP, that is from statsmodel.compare import LJIP. That is LJIP is basically this test, that is this comma, this result, whatever the result. Basically, this JB test is giving you the 4 values. The values of all, means this JB, chi-square, skew, kurtosis, and that's why we are GPing it to create this type of ordered pair. So in this case, this third bracket is basically a list, and this first bracket is basically a tuple. In this case, a JB value, this chi-square value, skew value, kurtosis value. Okay. Next one is this omni test. In this omni test, what I am doing, that is statsmodel.sm.stats.omni normal test. I'm passing this model residual ID. So it is giving this chi-square test, 2-tail probability. Same way, I am checking this test for the multicollinearity, that is called the conditional number. Test for the heteroscedasticity and this homoscedasticity. This means in a heteroscedasticity, the variance is changing continuously. Always keep in mind. That is this Lagrangian multiplier testing, that's P value, F value, FP value, etc. And this Goldfield quantile test we are doing. And finally, we are doing this Harvey-Collier multiple test, etc. Now, in a day, it is extremely difficult for any students to understand all the statistical testing. So I will give you a handout. In this handout, even if you get time, you go to this SQL documentations, you will get all the tests. You read carefully what exactly the purpose of this test. And this finally, we are getting this leverage versus the normalized residuals squared error. That is the normalized residual square along x-axis, and this leverage along these means along y-axis. And if you plot these residuals, this will be the data points corresponding this data points row numbers. It is given, that is annotated. You can check it here. Now, this is in a very brief way multicollinearity diagnostic plot, because multicollinearity diagnostic plot we will do repeatedly. Another one is very important, that is, let me start the Jupyter. In this Jupyter, what I will do, I will discuss about this MLE, how to use this MLE. MLE is very, very important for all of you. The only stuff is left, that is the Bayesian regression. In this Bayesian regressions, what you will do, that is Bayesian regressions means we will use this Bayesian approach. That is, Bayesian means this conditional probability. This conditional probability we will use to find out, you know, the dependent variable and this independent variable, etc. So if you open this one, hopefully it will open. Yes, let me share this one. Great. Now this is the last topic. We need to explain this one. Are you getting this one? This linear regressions with this MLE. Hello?
Yeah, I can see it.
Okay. The linear regressions with this MLE, this thing is, I am considering this expression, that is y is equal to beta 0, beta 1, x1, epsilon 1, y1, y2, y3, yn. These are the data points we are getting from the data sets. And beta 0, this is the means this is the constant term. The intercept you can consider, that is beta 1 is basically this gradient, okay, or the slope, and this epsilon 1, epsilon 2, epsilon 3. These are basically this error term. So what is our concept? The concept is this epsilon will follow the normal distribution with the 0 and its sigma square, the standard deviation. So the mu, this mean of the data points must follow this expression, that is the beta 0 plus beta 1, beta I plus xi. Now, if one single point follow the normal distribution, this entire data set that is called this cumulative distribution functions must follow the product of all the normal distribution functions, that is the product of n yi, the data points, given that the parameters are given, that is the mean mu I and this variance sigma square. Now this is nothing but the likelihood. The likelihood function L, the parameters mu I sigma square, and this is yi, this is equal to this distribution n yi mu I sigma square. That is, this sign is means the product, means n1 y1 sigma mu1 sigma square multiplied by n2 y2 mu2 sigma square this way. And finally, what we need to find out, that is, what is the PDF, the probability density function. So if you can recall this previous class, that is the probability density function and the probability mass function. Probability density function for the continuous variable, probability mass function for the discrete variable. Probability density functions, continuous random variable when we are considering. That is Py is equal to 1 upon square root of 2 pi sigma square e to the power y minus mu. I think we need to increase this. Okay, now you can check. That is y minus mu whole square divided by 2 sigma square. Now, this is these expressions. If you take the product of all value of, this is probability for y1, probability of y2, and all of them are independent. So their joint probability definitely will be the product of P probability of y1 multiplied by probability of y2, probability of y3 this way. So this will be, the product of these probabilities. So this is nothing but the likelihood. And if you take out this constant term here, so it is nothing but 1 upon 2 pi sigma square to the power n, and the product of all this term. So it will be 1 by 2 pi sigma square to the power n e to the power summation of, because this is nothing but e to the power y1 minus b1 whole square divided by 2 sigma square multiplied by e to the power minus mu2 y2 minus mu2 whole square divided by 2 sigma square. So e to the power x1 multiplied by e to the power x2 is nothing but e to the power x1 plus x2. So this is nothing but e to the power summation of yi minus mu I whole square divided by 2 pi sigma square. So if you take ln base e, means log base e, that is logarithm both sides, so it will be log likelihood, logarithm of this one, log of this one, because product of log of AB means log of A plus log of B. So this is log and plus log of this. So if we simplify it further, you will get this is equal to, I should put this logarithm sign, is log of likelihood, that is minus of n by 2 log of 2 pi minus n by 2 log of sigma square minus summation I is equal to 1 to n yi minus mu I whole square divided by 2 sigma square. Now, what is the value of this one? That is I is equal to 1 to n yi minus mu I whole square divided by 2 sigma square is equal to y minus x beta transpose multiplied by y minus x beta divided by 2 sigma square. So next is I am importing numpy. I am importing matplotlib.pyplot is plt, import math function. Math function means you will get cosine, sine, tan inverse, then cos inverse, sine inverse, all these functions you will get, power, etc. And another important term is scipy. NumPy we discussed, this is scipy. Scipy is basically for this optimizations purpose. So from scipy.optimize import minimize. This minimizations function, maximizations functions, these are basically important, to minimize a function, to maximize a value. Now what I'm doing, I'm initially considering, I'm generating the data. So I'm considering this number of observation, let it be 200. B0 is 5.67, B1 is 1.065, X is numpy array of range 0 and 1, Y is equal to beta 0, beta 1, X. Error mean is 0, error standard deviation is 5, error is equal to, I am creating this error will follow the normal distribution as per this OLS. So a numpy dot random the normal distribution error mean that is 0, error standard deviations, and how many data points you need to create? 200. So that's why I'm passing n. So YG is this the predictor which will follow the Gaussian distribution. That's why G, that is beta 0 plus beta 1x plus the error term. Now what I will do, this plot figure size is 14.7, that is this large pixel I'm giving. This plot scatter plot initially, that is X variable, YG, alpha is basically, is basically, let us consider you have the blue color, and alpha is means you are mixing this white color. So the color of the blue will basically reduce one after another. So the edge color I'm considering blue, and I'm giving its label, that is this one. Scatter is basically X comma Y, alpha is equal to 0.5, edge color black, label without Gaussian error, and plot this one, plot X label, plot Y label, plot legend, plot title, and plot show. So you will get this one. This is the Emily regressions finally. And the next is log likelihood. If you do this, basically this is the function, this is log likelihood, this parameter X comma Y, beta 0, beta 1 variable is parameters you are passing. This n is the length of Y, term 1, term 2. Term 1 and term 2 is basically this term you are calculating. You have already calculated this one. This is term 1, that is n by 2 log of 2 pi, then n by 2 log of sigma square, and this is this last term. So you will get the term 1 and term 2. Then XR is basically the reshape, -1 to 1. N is this concatenating. Reshaping means you are transposing this matrix. That's numpy concatenate means you are adding 1 to create the design matrix. That beta matrix means a beta vector you are creating, and you are creating its transpose. Then you are creating this term 3, that is y minus x dot b dot t, that is x y minus xb transpose dot of y minus xb divided by twice of var, and then you are returning this term 1 plus term 2 plus term 3. And what you are doing, you are creating some bounds, that is 0 to none, and then you are calling the minimize function, that is logarithmic function. Negative logarithmic hood means the maximize function is plus, the minimize function is negative of this. So that's why you are putting a negative sign here in front of this term 1, term 2, term 3, and you are giving a seed value, that is arguments, that is x and yg, that is the x value, this independent variable, yg is this Gaussian, the determinant. Method is LBFGS bounds you are passing, that is b and ds, and then you are printing this beta 0, beta 1, and sigma square, you are printing this residuals dot x. So you will get this beta 0, beta 1, sigma square, and it will print this, the beta 0 value is this, beta 1 value this, and sigma square this. This is all about how to use this maximum likelihood in case of this linear regressions. So always remember, so if it is follow these Gaussian distributions, and if you use this maximal likelihood, so you will get this exact same result like this ordinary least square. So that's all in brief in the students class. So if you have any questions or anything, so you can ask me. Otherwise, you can send this email. So thank you very much for attending my class.